Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study associate elements in a ring. I have written here definition, we shall see the definition, examples, a result and some problems we shall discuss in today's lecture. The definition is, let R be a commutative ring with unit element. Two elements A and B are said to be associates if B is equal to A into U for some unit U in R. We have studied in our earlier lecture what is a unit in a ring. The element is unit if it has multiplicative inverse, or every elements which has multiplicative inverse are units in a ring. And therefore, if B is expressed as A into U, then A and B are associate elements where U is a unit. For example, see the first example here I have written is in ring of integers Z with usual addition and multiplication, there are two units, that is 1 and minus 1. These are the only two units in ring of integers, because these are the elements which has multiplicative inverses. That means the inverse of 1 is 1 itself and inverse of minus 1 is minus 1, and therefore these the elements are units in the ring of integers. And therefore what will be associate of an integer in the ring of integers? If you consider A is integer, then its associates will be A itself and negative of A, because we can write A as 1 into A and 1 is unit, and that means it is written in this form, B is equal to A into U. Here U is 1. It is commutative, so it can be written as B is equal to AU or UA. And you see, if A and B are associate elements, then we can write B is equal to A into U, or A is equal to B into U, or say that can be considered as U1, and here it can be considered as B into U2, where U1 U2 are units. And thus these are the two elements which are associates. That means the relation is A and B are associates of each other, and thus here A is associate of A itself and A is associate of negative A, because A can be written as minus 1 into minus. Here U is minus 1 and here U is 1, because these are the two units in the ring of integers. And for example, 5 and negative 5 are associates, or say minus 5 and 5 are associates, or minus 5, every element is associate of itself because it is written as 1 into that element, and thus additive inverses are associates in the ring of integers. Now, another second example we shall consider is the ring of real numbers, which is denoted by R, addition and multiplication. So every non-zero element is a unit in the ring of integers. We have seen earlier that every non-zero element is a unit, because every non-zero element in the real numbers has multiplicative inverse, and therefore every non-zero element is a unit. The meaning of unit is simply the element which has multiplicative inverse. And for AB belongs to R, we can write B as, this can be written, see this equation, AB is equal to B upon A into A, where A is not equal to 0, because we have written B, the ratio as B upon A, or division here, and therefore A must not be 0. And we can take B upon A is a real number, it is a real number, and that can be taken as U, and therefore this is also in this form, B is equal to A into U, and therefore these two elements B and A are associates. And or in other way, any two non-zero elements, real numbers, are associates of each other, are associates. For example, 3 and 5 are associates. because we can write 3 as, say, 3 upon 5 into 5, and where this u is 3 by 5. 3 by 5 is a non-zero real number and it is a unit. So here u is 3 by 5, and therefore 3 and 5 are associates. So any two non-zero real numbers can be written in this form, or see here b is written as b upon a into a, and therefore a, b are associates. Condition is it is non-zero, a is not equal to 0. So this is the meaning of associate elements. The two elements are associates if one is expressed as unit into the other element. Now we shall see this result as a lemma. Let R be an integral domain with unit element, and suppose that for a and b in R, both a divides b and b divides a are true, then a is equal to ub, where u is a unit in R. A is equal to ub means a and b are associates, or that means if a divides b and b divides a, this implies a and b are associates, or in other words, if the two elements divide each other, then the two elements are associates. So for example, in this first ring we have, say, 3 divides minus 3 and minus 3 also divides 3. So therefore 3 and minus 3 are associates, and here any two elements, non-zero elements, non-zero real numbers divide each other, and therefore they are associates. Or for example, in real numbers we have 3 divides 5, because 3 is written as 3 by 5 into 5. So 3 is a multiple of 5, and that means 3 divides 5, and also 5 divides 3. 3 divides 5 and 5 divides 3. Here we can write 5 as say 5 by 3 into 3, and here we can write 3 as 3 by 5 into 5. So therefore these two are associates, and here in integers only the additive inverses are associates, negative of each other are associates, and here any non-zero real numbers are associates of each other, and they divide each other in real numbers. So division in a real number happens for every non-zero real numbers pairs, but in integers we have the relation of this type only. An element divides itself, or an element integer divides negative of the integer, and the result is a divides b, b divides a, then a is equal to u into b. That we shall prove. Now we can use the definition of divisibility. Since a divides b, we have b is equal to xa for some x, for some x belongs to R. This is the definition of divisibility in a ring. And also what is given, b divides a. Also b divides a, and this implies a is equal to y into b. A is multiple of b, and for some y belongs to R. Now we want to write the expression for a, and thus therefore a is equal to yb. But what is b? B is x into a. We combine these two. A is yb, and in place of b we write it is x into a. Y x into a. And what this gives is, or this may also be written as the relation for b. B can be written as xa and then xyb. So in that way also we can write. and this implies A is equal to yx into A. So these are the elements of integral domain. So cancellation law holds in integral domain, and therefore by cancellation law A cancels and we get 1 is equal to ix. By cancellation law we get 1 is equal to ix, and what this shows, if x into y or y into x is equal to 1, then x and y are unit. That is our earlier definition, unit in array. If AB is equal to 1 means A and B are units. Therefore, y is a unit. Y is a unit, and in R. X is also a unit. X is also a unit, and both are unit. X and y both are unit, but we need y, and therefore we have y is equal to A is equal to ib, and we want to write expression for A, and we have A is equal to yb, and this proves the result taking y is equal to u. So this proves the lemma, and hence this is the result. Or thus, therefore A is equal to ub, where taking y as unit, y is equal to u is a unit. So thus this proves the lemma. If A divides B and B divides A, then A can be written as ub, where u is a unit in R. Now next we shall consider some problems, and see, we have defined associate relation, and now we shall prove that this associate relation is an equivalence relation. So I shall write it as a problem. Our first problem as let R be a commutative ring with unit element. Two elements A and B are associates of associate elements A associate B. If A comma B belongs to R, the relation A is associate of B. Is an equivalence relation. This we shall prove. And we have written definition here. A and B are said to be associates if B is equal to A into U. And this relation is we want to prove equivalence relation. So what is the meaning of equivalence relation? A relation which is having three properties, that is reflexive, symmetric and transitive, is equivalence relation. And we shall prove this associate relation is having these three properties. So first we shall denote this associate. A is associate B. Let AB belongs to R that are given. let A comma B belongs to R, where R is commutative ring with unit element. We denote A tilde B if A and B are associates. That is B is equal to A into U for some unit in R. And now we will consider the first condition, that is the relation is reflexive. So what is the reflexive relation? We say that we must have A must be associated with A or A tilde A. So we have A associated with A, or A is associate of A. Since we can write A is equal to 1 into A, where 1 is unit. 1 is actually identity and it is also a unit, and therefore this satisfies 1 is equal to A into U, that is A is equal to 1 into A, and therefore A is associate of A. That is simple. Now second is symmetric relation, and we shall consider for symmetry we have to show that if A is related to B or A is associate of B, then B is also associate of A. That we shall have to prove. That is the second property for equivalence relation. Second condition, symmetric. Let A and B are associates, and that means B is written as AU for some unit U in R. So this implies B is equal to, we are using the definition A into U for some unit U. U belongs to R, and from this relation we can write as we can post multiply. U is a unit. U is a unit, and unit is that element which has multiplicative inverse. So this has multiplicative inverse. So we multiply both sides by its multiplicative inverse, means U inverse of U. And that means it will be B into inverse of U is equal to A U into inverse of U, multiplying both sides by inverse of U. And this implies B into inverse of U is equal to the product of element and its inverse is identity, and therefore here the right side will be only A into 1, or that is A is equal to U inverse into B. A is equal to U inverse into B, or B into U inverse. Anyway you can write, it is commutative. B into U inverse. And this is a unit, because if U is unit, its inverse is also unit. This implies B is associate of A. B is associate of A. These are interchanged, since U inverse is a unit, as U into U inverse is equal to 1. If the product of two elements is 1, then the two elements are units. So this proves the symmetric property. A associate of B, then B is also associate of A. Now what remains is transitive property, and that is third relation we shall consider. For this we shall let A is associate of B and B is associate of C. then what we want to prove is A and C are associates. That we want to prove. And so we shall apply the definition. A associate of B means B is equal to A into U, and here two relations are there, so we shall use U1 and U2. So this implies B is equal to A into U1 and C is equal to this will be B into U2, where U1 U2 are units in R, and from this we can express C. We can express C as combining these two. C is equal to B U2, but what is B? B is A into U1, and therefore this will be A into U1 U2, and you see U1 and U2 are units and their product is also unit. So therefore this implies C is equal to U1 U2, that can be written as U3 also. So I shall write here, this implies C is equal to A into U3, where U3 is equal to U1 U2 is a unit in R, and this implies A is associate of C. A is associate of C, and you see A is associate of B, here A is associate of C, and thus A is associate of B, B associate of C implies A is associate of C, and thus the relation is transitive, and thus from 1, 2, 3, 1, 2 and 3, A associate of B is an equivalence relation. So that means if A is an associate of B, B is also associate of A. And one more problem we shall consider for greatest common divisor. In a Euclidean ring R, if G1 and G2 are greatest common divisors of A and B, then G1, G2 are associate of each other. That we shall prove. If G1 and G2 are greatest common divisors of A and B, then G1 and G2 are associates. All elements are in the Euclidean ring R. So we shall prove this as we shall solve this as, let A, B, G1, G2 belongs to R. And what is given is G1 is greatest common divisor of A and B. Also G2 is greatest common divisor of A and B in R. Now we know that the greatest common divisor is unique in the ring of integers. The greatest common divisor is unique in the ring of integers, but it is not unique, or it is not actually well defined in the ring of real numbers, because in the ring of real numbers we know that any non-zero integer divide each other, and therefore there is actually not a unique greatest common divisor in the ring of real numbers. And if we suppose there are two greatest common divisors of same pair of elements a and b in R, then G and G2, these two greatest common divisors are associates that we have to prove. So here let G1 be the greatest common divisor. Divisor of A and B. So that is given, both are greatest common divisor of A and B. By definition of greatest common divisor, it is first a common divisor, that then this implies, say, G1 divides A, G2 divides G1 divides A and G1 divides B. It is common divisor. And what is the second condition of GCD? There are two conditions of GCD. If there is any other common divisor, then that common divisor divides the greatest common divisor. Now here G2 is greatest common divisor, means it is a common divisor. So taking G2 as common divisor, then G2 divides G1. So this is the relation. Taking, if G1 is treated as greatest common divisor, then G2 divides G1. So we have G2 divides G1, and when G2 divides G1, by divisibility relation we can write, this implies G1 can be written as a multiple of G2, and that multiple may be taken as say any element, U1 into G2 for some U1 belongs to R. Similarly, G2 is the GCD of, is a GCD of A and B, and this implies G2, see this implies G1 is common divisor, and therefore that G1 divides G2. Here we are considering G1 is greatest common divisor and G2 as common divisor, therefore G2 divides G1. Here we are considering G2 is the GCD of A and B and G1 is common divisor, so therefore G1 divides G2, and this implies G2 is multiple of G1. So that can be written as G2 is equal to U2 into some element U2 into G1 by definition of divisibility. This is multiple, so G2 is equal to an element into G1 for some U2. U2 belongs to R. We don't know what are U1 and U2, but there exist these elements. And now what we shall combine is these two relations. So thus G1 is equal to, so what we will have is G1 is equal to or we may write this as 1 and 2, from 1 and 2. We can write G2 is equal to from 2, U2 G1, and this is U2. What is G1? G1 is U1 G2. And thus now you see this can be grouped U1 U2, and by cancellation law we get we get 1 is equal to u to u1. And what this shows, both u1 and u2 are units. Therefore, u1, u2 are units. Units in R. And once this u1 and u2 are becomes units, see we have g2 is equal to u2 g1, therefore g1 g2 are associates. A and B are associates if u is unit, and this shows that, and g2 is equal to u2 g1. So therefore g1 and g2 are associates by this definition. So this is the meaning of associate elements. In simple words, two elements are associates, they divide each other, or one is expressed as second into some unit in the ring. And thus we have we have studied associate elements in a ring. I hope you can understand this. Thank you for watching the lecture.